Good morning everyone. In today's video lecture, we'll learn about liquid-liquid extraction under the course of pharmaceutical analysis. So let's start. So liquid-liquid extraction is a versatile and dependable separation technique wherein an aqueous solution is easily brought into contact with another organic solvent exclusively immiscible with the former, so as to effect a legitimate and actual transfer of either one or more solutes into the latter. The separation technique is superior to others due to ease of use, faster extraction time, decreased volume of solvent, and superior ability to concentrate the analytes. Invariably, such separations may be performed by shaking the two liquids in a separatory funnel for a few minutes and may be extended either to large quantities of pharmaceutical substance or trace levels. Liquid-liquid extraction are usually accomplished with a separatory funnel. The two liquids are placed in a separatory funnel and shaken to increase the surface area between the phases. When the extraction is complete, the liquids are allowed to separate with the denser phase sitting to the bottom of the separated funnel. So in liquid-liquid extraction, what usually we perform is that whenever we are extracting our contents from any roots or leaves of some medicinal plants, then utilizing this extract we usually perform this liquid-liquid extraction, because this extract is having some polar compound, some non-polar compound, some intermediate polar compound. Then obviously you need to isolate the compound based on their polarity. Okay, so that is why usually liquid-liquid extraction is performed. Because yes, for example, I have given you some methanolic extract of some leaves, okay, of some medicinal plant. Then yes, yeah, in this methanolic extract you may have some other lipophilic contents, okay, lipophilic compounds. To isolate the lipophilic compounds, methanol is not necessary. Methanol is not uh, okay, because you need to use some other non-polar solvents like hexane. Then what will you do? You will mix this methanolic extract, okay, with some hexane, and just mix them, and you can have a separate layer of methanol and hexane. That means your compound based on its lipophilicity would be differentiate between two solvents. Okay, so this is the overall rationale for undergoing the liquid-liquid extraction, because this is the very beginning step of analyzing or phytochemistry, okay, or having separate fractions of our extracts. Okay, so you can see here, as I have told you earlier, that for example, aqueous solvent and organic solvent, this is your compound. Okay, whenever you are mixing your compound in these solvents, then based on its distribution potential or some partition coefficient or some other physicochemical property, the compound would be distributed. Okay, because this compound is having some polar compounds, non-polar compounds, intermediate polar compounds. Okay, they would be get distributed in that manner. You can see the polar black compounds have been distributed in aqueous phase, and the green non-polar compound has been mixed up with the organic solvents, so they have become separated. In the case of pharmaceutical chemicals that are mostly organic solutes, the liquid-liquid extraction system may very often make use of two immiscible organic solvents instead of aqueous organic type of extraction. Liquid-liquid extraction can also be used to remove a component from an organic phase by adding an aqueous phase. You can see here we sometimes use separating funnel for separating the compound, liquid with the lower density, liquid with the higher density, then funnel tap, then container. Okay, they would be separated, and the both of them would be isolated or separated using the container. The solvent, this is the light phase, this is the feed solution with the mixture of solutes. Then upon mixing, you can say you can have phase separation. Okay, and this extract and this extract with solute. Okay, you see. Then the raffinate with non-extracted solute. Okay, so usually this is our extract which we need importantly, and this is the raffinate which we usually don't need, but yes, it may be used for further analysis. Okay, phase 1, phase 2, the oil phase and the water phase, based on their density, get separated. If you add any compound, they would get distributed between them. However, there are a number of extraction processes like infusion, decoction, maceration, percolation, digestion. Actually, all of them has been discussed in your physical, in your previous course, like pharmacognosy. Okay, so infusion, uh, it can be done by fresh infusion or concentrated infusion. Then maceration, it can be of simple maceration, maceration with adjustment, multiple maceration. Then percolation, uh, it can be simple percolation, percolation process for concentrated preparation, then continuous percolation process. Okay, then the digestion. Please see the differences among them, and see my several other videos in this channel if you want to have a great description of this content. Now let's learn commonly used terms in liquid extraction. First of all, feed phase. The feed phase is the initial mixture or solution that contains the target compound to be separated. It typically consists of solute, the carrier solvent, and other impurities. The extract phase. The extract phase refers to the phase that contains the solvent and the desired solute after extraction process. It is the phase enriched with the target compound which has been transformed from the feed phase into the extractant solvent. Then refinite phase. The refinate phase is the remaining phase after the solute has been partially or completely extracted. It primarily consists of the carrier solvent from the feed and the impurities or solute that are not extracted. Then solvent phase. The solvent phase is the immiscible liquid phase used to selectively dissolve the target compounds from the feed phase using the extraction process. The solvent phase must have high affinity for the solute and should be immiscible or only sparingly miscible with the feed phase for effective separation. So I have already discussed them in previous slides. Now, liquid extraction principles. What is the basic principle or theory behind this extraction? I have already discussed. Actually, distribution coefficient. The distribution law or Nernst equation is the basic principle for liquid extraction, because any compound would get distributed among between water or organic phase. Okay. So feed phase containing component, for example I, which is to be extracted, addition of a second phase, solvent phase, which is immiscible with the feed phase, but component I is soluble in both phases. Some of the component is transferred from the feed phase to the solvent phase. After extraction, the feed and the solvent phase are called refinate and the extract phase respectively. Normally, one of the two phases is in an organic phase while the other is an aqueous phase. Under the equilibrium condition, the distribution of absolute I over the two phase is determined by the distribution law. After the extraction, the two phases can be separated because of their miscibility. Components I is then separated from the extract phase techniques such as distillation, and the solvent is regenerated. Further extraction may be carried out to remove more components I. Okay, actually any compound would get distributed between the two phase. So this is the basic theory. Nernst distribution law or partition law states that at constant temperature a solute distributes itself between two immiscible solvent only in particular ratio. So you can see the ratio here. Extraction is an equilibrium process, and therefore a finite amount of solute must be in both phases, necessitating the processing steps or manipulating of the chemical equilibria. The partition law offers the following two limitations, namely it's solely applicable to very dilute solution. It doesn't hold good when the distribution substance encounters association or distribution in either phases. So here are some classification of commercial extractors. Usually in our lab we usually perform this by small scale, but in commercial scale different extractor is used. Just go through them. Okay, now we can easily understand that solvent selection is one of the critical step in liquid extraction, because you have some more solvents like methanol, you have acetonitrile, you have acetone, you have isopropyl alcohol, you have hexane, you have dichloromethane, water, lot of solvents you have. But the question is how you will select these solvents. Okay, Usually for liquid extraction, we begin with some some non-polar components like non-polar solvents like hexane. Okay, then upon extraction by hexane, then we come into some polar solvents, intermediate polar solvents like dichloromethane or chloroform. Then we go into ethyl acetate. Okay, so solvent selection is one of the critical steps. So there are some criteria for this. First of all, miscibility. Solvents defined as miscible if two components can be mixed together in all proportions without forming two separate phases. Solvent should be immiscible. Then density. Density of extraction solvent is an important parameter of solvent selection. Solvents that are more dense than water will form the lower layer of the solvent pair when mixed together, while solvents that are less dense than water will form the upper layer. For example, ethyl ether has density of 0.7133 gram per ml at 20 degrees Celsius and would constitute the upper phase when combined with water, which has density of 0.9982. Density of chloroform is 1.48 at 20 degrees Celsius. Therefore, water would form the top layer in the water chloroform solvent pair. Actually, density may differ solvent by solvent, so just keep this into consideration. Okay, because we usually don't use solvents which are having same density because it will create some interferences. Okay, so it's better to use solvents which are having a greater difference in their density. Okay, so lighter liquid, denser liquid is here. This is the separating funnel. Okay, so water and hexane, they are less prone to emulsion form. Okay, but whenever we are using water and benzene, you can see their solubility much more closer. Okay, then should not be used in the extraction, otherwise they may form emulsion. Okay, we'll discuss this later. Then solubility. Although immiscible solvents may form two visibly distinct phases when mixed together, they are often somewhat soluble in each other and will in fact become mutually saturated when mixed with each other. For example, 1.6% of the DCM is soluble in water. Conversely, water is 0.24% soluble in dichloromethane. So should be insoluble with each other. When the phases are separated for recovery of the extracted analyte, the organic solvent layer will contain water. Similarly, after extraction, the depleted aqueous phase will be saturated with organic solvent and may pose a disposal problem. Now, let's discuss factors that influence the solvent extraction. First of all, effect of temperature. The effect of temperature on the partition coefficient may be estimated conveniently from its effect on the solubilities of the substance in the two respective solvents. So consideration, solvents used should be immiscible and the concentration of the solutes are fairly low in both the phases. So temperature should be constant throughout the process. Then effect of pH on extraction. Generally, it has been found that the organic acid and bases in solution may exist as equilibrium mixture of their respective neutral as well as ionic forms. Thus, these neutral and ionic forms may not have the same identical partition coefficient in a second solvent. Therefore, the quantity of substance being extracted solely depend upon the position of the acid-base equilibrium and ultimately upon the pH of the solution. In conclusion, it may be observed that the pH of an extraction system must be selected in such a fashion so that the maximum quantity of the analyte is present in the extractable form. That obviously suggests that the analyte should always be in the form of either a free base or free acid. Emulsion problem encountered in extraction. Emulsion may be defined as the dispersed system containing at least two immiscible liquid phase and the system is stabilized by emulsifying agent. Sometime during liquid-liquid extraction, you may appear some emulsion form as a separate layer. Okay. The effective and meaningful extraction of a solute is rendered almost impossible when there is an emulsion formation during the extraction process. Emulsion formation makes the separation of the two phases difficult. Actually, emulsion formation is a frequent and serious problem when dealing with the extraction of drugs from biologicals as well as pharmaceutical formulations. So you can see here how emulsion has been formed. This is a clear separation, very good, but here you can see emulsion formation. Okay, it has some cloudy. This is the emulsion formation and it is not good. We don't expect this. Okay, so we can see that good emulsion, this is the good emulsion, and this is coalescence, this is creaming, then this breaking, this flocculation. Actually, we don't want emulsion. Okay, factors that can cause slow coalescence emulsion. Okay, because we don't want emulsion in our liquid extraction. So which factor can this can form this emulsion? The breaking of an emulsion could be slow process. There are a number of factors which may be responsible for the slow coalescence of an emulsion, namely finely divided powder of albumin, gelatin, natural gums have a tendency to coat the droplets formed in an emulsion, which ultimately prevents them from coalescing. Easily surfactants decreases the interfacial tension or surface tension between the two immiscible liquids, which help in stabilizing an emulsion. Then ionic species may get absorbed at the interface of two immiscible layers, resulting in the formation of net charge on the droplets. Because all droplets shall essentially bear the small similar charge, naturally they will repel one another, thereby preventing coalescence. So it shows the liquid two-phase system vigorously mixed. In fact, there are many natural and synthetic substances that profusely incorporated in the formulation of drugs, which are found to stabilize emulsion either by coating the droplets or by minimizing the interfacial tension, namely coating of the droplet, minimizing the interfacial tension. Okay. Prevention of emulsion formation. It has been observed that once an emulsion is formed, it is difficult to break the emulsion. Therefore, it is absolutely necessary to concentrate to the following guidelines as far as possible in order to avoid forming emulsion. This is the most important thing. Otherwise, you will not have clear solution. Okay. So first of all, very cautious or gentle agitation and employing a sufficient large liquid-liquid interface provide a reasonably good extraction. When the liquid to liquid layers have large contact surface in an extraction process, vigorous or thorough shaking of the two phases is not required at all. So whenever you will mix one solvent with another, then please make sure that this is stainless steel. Your separating funnel is stainless steel. Okay, it's not vibrating or you are not shaking them, because uh, whenever yes after overall settle down, if you just cause some vibration or you have some mixing, then yes, this may form emulsion. So always prefer gentle agitation. Number two, the removal of any finely divided insoluble materials in a liquid phase must be done by filtration before carrying out the extraction process. Number three, always prefer and use such solvent pairs that have large density difference and have high interfacial tension. I have already discussed this because you have similar density. If you have similar density of solvents, then obviously they may form some emulsions. Okay. Then when performing extraction from water, always ensure not to work at extreme pH and particularly at higher pH range to avoid emulsification. Okay, because just try your best to avoid extreme pH. It can be for any other assay in UV spectroscopy, in fluorometry, in liquid extraction, in non-aqueous titration. In each other case, please avoid extreme pH. Always try to work in 5 to 7 or 5 to 8 pH. Okay, a major convenience of this method is the extreme pH. In case of acute emulsion problem, substances like ion exchanger, alumina, or silica gel are used specifically to resolve the problem by adsorption of the emulsifying agents. So these are the common approaches for prevention of emulsion formation. Now we will see the process of breaking an emulsion. Suppose your emulsion has already been formed. Then what should you do? In previous slides, we have seen the prevention of emulsion formation. Now we'll see the curative action for emulsion formation, for breaking the emulsion, because it is undesired and unexpected. Okay. First of all, mechanical means: centrifugation, addition of monovalent and divalent ions, ethanol or higher alcohol, silicon deforming agents, sudden cooling of emulsion, then altering the ratio of the solvents. First of all, mechanical means: coalescence may be eliminated by mechanically created turbulence on the surface of the droplet, either by passing the emulsion through a bed of glass wool or simply by stirring with the help of glass rod. Then centrifugation. In cases where the densities of the two liquids are appreciably different, coalescence may be removed by centrifugation. Then addition of monovalent and divalent ion. This ion will form chelates. Okay. Relatively simple emulsions are broken by adding monovalent salts like sodium chloride, whereas charge stabilized emulsions are specifically sensitive to the divalent ion like calcium magnesium. Then ethanol or higher alcohol, addition of small quantities of ethanol or sometimes higher homologous alcohol to remove the coalescence. Okay. Then silicon defoaming agent, a few drops of silicon defoaming agent sometimes help in the breaking of an emulsion. Then sudden cooling of emulsion or thermal shock, sudden temperature drop or freezing of an emulsion mostly enhances the interfacial tension between the two immiscible phases, thereby causing coalescence. Lastly, altering the ratio of solvents. Coalescence of an emulsion may also be achieved either by altering the ratio of the prevailing dispersed phase or even by partial evaporation of the solvent. So let's discuss the common applications of this method. First of all, separating of element concentrated impurities, clearing of the basic components from impurities in the process of synthesis of substance of drugs, then definition of the basic components from impurities, then for identification and quantitative definition of chemical agent or substance marker in the process of analysis of phytogenesis of drug, then increase of sensitivity and selectivity of the reaction, then studying the formation of constant complexes, then studying of substance condition in a solution, then separation controlled by pH which control ionization and complex formation, then cleanup before analysis. Okay, so these are the basic applications of liquid-liquid extractions. Okay, this is the overall lecture from liquid-liquid extraction. In this lecture, we have already seen the methods, steps, advantage, disadvantage, applications of liquid-liquid extraction, along with practical implications of this. So, if you have any confusion, please comment in the section. Thank you.